Professor Keshav Pingali did his undergraduate work at IIT Kanpur at the time when Kanpur was the cream of the IITs in India.
It still is.
Still is, really?
I think so.
Good. I thought so also, but I was told that. Then he went on to MIT. You were Arvind's first student, yes?
Yeah.
Yeah, where he was Arvind's first student. He's done brilliant work across the board, first at Cornell, and for the last, 10 years now?
9 years.
At the University of Texas at Austin, where he holds the most prestigious endowed chair in the computer science department. And I will just sit down and shut up while I learn from you. Thank you, Keshav.
Thanks for that introduction. Yeah. Can you hear me at the back?
Yes.
Okay. Well, it's not often in life that you get to do something that's both an honor and a pleasure. So today is one of those occasions for me. It's a great honor to give this keynote because the SAMOS workshop is now a conference and it's now in its 15th incarnation and people everywhere know about it. And there are not many workshops and conferences that actually survive 15 years. And so that says something about the quality of this conference. So I'm very pleased to be here. But it's also a great pleasure for me to be here because, like so many others in this room, I counted Stamatis as one of my friends. As Yale mentioned, before I moved to UT Austin, I was at Cornell. And Cornell, as you may know, is not very far from IBM Endicott, which is where Stamatis used to work. And so he used to come up to Cornell roughly once a month. He spent a semester visiting my group and a group in ECE. And so over the years, I got to know Stamatis and developed a deep affection for him, like so many people in this room. And so it's a great pleasure for me to come to this island where he was apparently born and brought up, and to remember him along with all of you. So I'm going to be talking about some work that I've been doing since I got to UT Austin a while back. And what I want to do is to begin by reminding you of something that all of you already know. And that is that parallel computing has changed a great deal in the past 15 to 20 years. So certainly if you go back even further than that, back when I was a graduate student at MIT, as you mentioned a while back, parallel computing was done almost exclusively at these high-performance computing centers like TAC, the Texas Advanced Computing Center that we have at UT Austin that has some of the largest open machines in the world. For the most part, these HPC centers were used by computational scientists, computational engineers. What they did usually was to solve partial differential equations using approximation techniques like finite differences of finite elements. If they used finite differences, they ultimately ended up with dense matrices and operations on those dense matrices called stencil operations. If they use finite elements, the key kernel is a sparse matrix vector multiply that you need to do very fast if you want to get good performance. But in either case, regardless of what method you used, you ended up with what are loosely called structured data. And by that I simply mean matrices and vectors. And perhaps the most important point for the rest of our discussion is that the people who were doing this parallel programming were largely a bunch of physicists, chemists who learned a lot of computer science, and they devoted their lives to writing these codes, tuning the performance of those codes, and then porting these codes to different platforms. So these codes were like their babies. They spent a lot of time nurturing them and making sure that these codes were in good shape. Today we have a totally different world in parallel computing. So first of all, we have parallel devices everywhere. So all our cell phones, laptops, and so on and so forth are all parallel devices. They're also heterogeneous, GPUs, and so on. So cloud, mobile. So it's a very heterogeneous, ubiquitous parallel computing hardware, not just in these small number of high-performance computing centers. Another big change that's happened is that even though HPC remains very important, structured problems remain very important, a lot of the problems that we want to run on the cloud or mobile devices and so on deal with what I'm going to loosely call unstructured data. And for the purpose of this talk, it simply means graph computations. Now, some graph computations you can model as matrix computations, but a lot of the computations that we do on graphs involve dynamic graphs, where you're adding and removing nodes and edges, and that's kind of hard to model using matrices. So I think we should just embrace graphs and say graph computations, those are important, we need to support them. So that's what I'm going to mean by irregular or unstructured data. People use many different terms. And then again, the most important difference for what we're going to talk about is that instead of having a small number of elite scientists who devote their lives to writing these parallel codes, today, because of the ubiquity of the hardware that we have, there are millions of application programmers all over the world, even in countries like India and China and so on, who want to write applications for the parallel hardware that we have, but they want time to market. So that's very important for them. Programmer productivity, they don't want to have lots of employees writing these codes. So how do we prototype these applications quickly, get acceptable level of performance, get this application to market very quickly? So those are the kind of concerns that have suddenly become very important in the parallel computing world. So this has led to a change in our research agenda in programming languages, which is the area that I come from. And it's what I'm going to call the search for scalable parallel programming models. Scalable in the context of parallel programming usually means an application that runs faster if you give it more cores or more processors. That's not what I mean. I just mean something very simple. A scalable parallel programming model is one that's efficient enough and simple enough that millions of programmers all over the world are willing to use it to write their applications if you provide it to them. Okay, so how do you go about building these scalable parallel programming models? Well, what you need to do, of course, is to hide the complexity of all of this hardware that people like Yale continuously keep building into the hardware, right? How do you hide complexity? There's only one way that I know how to hide complexity, and that is through the use of abstraction. So what you need to do is to design the right abstractions, and then have these abstractions be implemented by a small number of expert parallel programmers that I'm going to call Stephanie programmers. So these Stephanie programmers are these elite parallel programmers who are going to implement these abstractions on different kinds of hardware. They provide these abstractions to the Joe programmers. So these are the ordinary programmers who may be domain experts. They write games, whatever it is, but they're not expert parallel programmers necessarily, and they rely on the implementations of these abstractions to get the efficiency that they want. So we originally called these two levels of programmers Joes and Steves, but some of you probably know Sarita Adve, and so I gave this talk, a version of this talk a few years back, and she took great exception to Joe and Steve. She said at least one of them has to be a woman. Well, you couldn't make the naive parallel programmers a woman, and so Steve essentially ended up becoming Stephanie. And now, interestingly enough, I'm starting to see Joe and Stephanie programmers even in DOE reports and things like that. So this is how Sarita has contributed to my research program in this way, among many other things. Okay, so Joe and Stephanie programmers, abstractions. Of course, the key question is, what should these abstractions be? So the danger, of course, is that if you make the abstraction level very high, so very close to the Joe programmer level, Joe's life is very easy. On the other hand, Stephanie's life might be very difficult because it might be very hard to implement these high-level abstractions efficiently on different kinds of hardware. And those of you who are old enough to remember the high-performance Fortran project that Ken Kennedy, who was one of the giants in our field, started about 20 years ago, well, that project ultimately failed, mainly because those abstractions that they came up with in HPF were at such a high level that we simply did not have the technology at that time to implement HPF efficiently, so nobody used HPF. Now, of course, if you went to the other extreme, and the abstraction level is too low, then Stephanie's problem is very simple. However, you haven't really done very much for Joe to hide the complexity of all the parallel hardware, so again, people are unlikely to use the abstractions you come up with. So what we need is basically some sort of a golden mean, so an abstraction level that can be implemented efficiently by the Stephanies, and at the same time hides enough of the complexity of parallel programming that the Joes are willing to use it because they also get the kind of efficiency that they want. Now, there's no unanimity of opinion about what these abstractions should be, but what I'm going to tell you about in the rest of my talk are the abstractions that we have come up with in my project, which we call the Kalalau project. So these are what we call data-centric abstractions. This is a term that we coined about 9 years ago when we started this, and now this term is catching on, and people have different abstractions, but they call them data-centric as well. So this is the age of big data, everything has to be data-centric. Well, we got there first. So data-centric abstractions for parallelism and locality. So in particular, there is a certain way of thinking about algorithms that I call the operator formulation of algorithms that I'm going to tell you about, which gives you a clue about how to build those abstractions. So I'm going to tell you about that. We've written lots of papers, but we also have software that you can download. So we have a scalable shared memory system that you can download and play with. It's all in C++. And there are people all over the world using it for doing things like FPGA placement and routing, multifrontal linear solvers for finite element methods, and there are companies like BAE and HP and so on who are also using it. So it scales to about 512 cores on an SUI origin, so it's quite scalable. And by the end of the year, we're hoping to have a GPU and a distributed memory version as well. So I'm going to show you a bunch of results towards the end of my talk, both from our results and other people's results, that tell you something about the scalability of this system. From what I've learned in the past couple of days, the power is going to go off in about 15 minutes. And so what I did was to have one slide which conveys the main lessons that we have learned painfully in the time that we've been doing this project. Like many lessons in computer systems, if you haven't gone through the pain of learning these things yourself, they might seem trivial or obvious. Some of them might seem incomprehensible. Well, as we go through this talk, I hope to make these lessons clearer. But basically, we've learned something about abstractions for parallelism, parallelization strategies, and applications. So let me go very quickly over them, and these points are basically things that I'm going to cover in the rest of my talk. So the way we started in this project was by using what we call computation-centric abstraction. This was the traditional way of thinking about parallelism. You look at the text of your program, and then you look for loops or procedure calls that you could do in parallel. It turns out that's not a very useful way of thinking about parallelism. So instead, we have data-centric abstractions, where the pride of place is really data structures, operations on data structures, and which operations you can do in parallel. So that turns out to be a much more useful way of thinking about parallelism than looking at the text of the program and trying to find loops or procedure calls that can be done in parallel. And this is something that I'll try and convince you about by using a few examples in the next few slides. Paralyzation strategies. So again, I come from the compiler world, and so we were told that if you really know what you're doing, either the algorithm writer or the compiler or some such piece of software is going to take your program, analyze it, build a dependence graph for it, and then at runtime all you have to do is to just execute your program in parallel following the dependence graph to make sure that all dependencies are respected. Now there were other parallelization strategies that people came up with, like for example speculative or optimistic parallelization, inspector executor, if you know what those are. But the feeling was that, well, if you really knew what you were doing, you should be able to build a dependence graph for your algorithm and then run in parallel based on the dependence graph. Today we realize that for a lot of these unstructured data problems, you can't actually build the dependence graph statically. And that's because you don't know the tasks and you don't even know dependencies between tasks because they're all functions of runtime data values. So instead you have to turn things around, and it's much better to start with speculative or optimistic parallelization as the baseline, and only when the algorithm has enough structure can you use some of these other techniques like static parallelization. So this again, of course, raises the question of what do we mean by structure, so I'll tell you about that as we go along. And then finally, how do you build applications? So the way we used to think about applications is that they're monoliths, and we used to do whole program analysis. So if you go back 10, 15 years, you'll find lots of papers about how people analyze a million-line program by building a big interprocedural control flow graph and doing data flow analysis across procedures and so on. Today we realize that's not a very smart way of doing things. Instead, programs must be layered. So in particular, data abstraction is essential not just for software engineering, but even for dealing with parallelism in any kind of a tractable way. So as I said, some of these things may seem a bit bizarre. What does data-centric mean? Some of these things might seem obvious. Well, I'll give you a bunch of examples to tell you what I mean by these things, and then we can have a discussion perhaps at the end about whether you believe what I'm going to tell you or not. Okay, so let's start with this idea of computation-centric versus data-centric abstractions. So this is the way we used to think about parallelism. Here is a piece of code, pseudocode over there on the left. What can you do in parallel there? So your first question might be, well, what does this code do? And the standard answer in the old days was, well, it doesn't really matter because compilers, runtime systems, architectures don't know anything about algorithms, so there's no reason for us to wonder about what the algorithm is. So then you say, well, how do I find the parallelism? Well, you look for loops that you can do in parallel. So sure enough, there is a loop over there. I think the pointer is not working, but you can see that while loop over there. And so what people used to do was to take that loop and see whether you can do the iterations of that loop in parallel. So what you would do is to compute the read and write sets of each iteration, and roughly speaking, if the read and write sets of each iteration are disjoint, then you can do them in parallel. Otherwise, you can build a dependence graph and execute according to the dependence graph. So this is an approach that worked very well in the old world of computational science applications where you were dealing with dense arrays. So in particular, in France, there was a lot of very nice work by Paul Foutrier and his co-workers. What they did was to come up with integer linear programming techniques for analyzing these kinds of loops, which dealt with dense arrays, and then find the parallelism over there. And they did a wonderful job, and a lot of us followed that work and expanded on it. Here, of course, there are no dense arrays, because this is an irregular, unstructured data problem. You're dealing with a graph. However, people came up with dependence analysis techniques for these kinds of data structures as well. So they're called points to and shape analysis techniques. Hundreds of papers written on these kinds of dependence analysis techniques. Even if you apply the most sophisticated ones, it turns out they all come back and say, there's no parallelism in this program because these iterations may be reading and writing the same set of values, so you can't execute things in parallel. So that led to two schools of thought. So some people said, well, what this means is that these kinds of unstructured data algorithms, there's no parallelism there, so that's why our techniques are not finding any parallelism. Other people who are perhaps more politically savvy said, what this really means is the National Science Foundation or the European Science Foundations should fund even more research on more sophisticated analysis techniques, because then maybe we can find the parallelism in these kinds of programs. Still others came up with techniques like thread-level speculation, where they use speculative execution in order to execute the iterations in parallel. However, for reasons that I don't have time to go into, misspeculation and the overheads of the ways that they did speculation, limited performance. Moreover, about 10 years ago when we started doing this work, people suddenly became aware of power and energy limits and so on, and the feeling was that speculation is going to waste even more power and energy on misspeculation, so thread-level speculation was a bad idea and so on. So this is what one would call computation-centric view of parallelism. This was the old way of thinking about parallelism. So now let me tell you about the new way in which we think about parallelism, and this is what leads to this data-centric point of view of thinking about algorithms. So what does this code actually do? Well, what it does is a very old algorithm that's called Delaunay mesh refinement. The input to this algorithm is a triangular mesh, like the one that I've shown over here. Some of these triangles in this initial mesh are badly shaped according to some shape criterion. It doesn't matter what that criterion is, but just by looking at, for example, maybe the triangle is too big, so there's a lot of discretization error there. So what you need to do is you look at the coordinates of the triangle, the 3 points, and from that you can classify it as either good or bad. That's what Pythagoras would say, right? And so, yeah, that's what we're going to do. So the bad triangles, the badly shaped ones, I'm simply going to color red. And the goal is to end up with a mesh that doesn't have any badly shaped triangles by doing a process of iterative refinement. So how does that iterative refinement work? Well, let me see if I can pull up a demo for you. So here is an initial mesh, and what I've done is to color all the badly shaped triangles red. What this code does is it picks one triangle at a time, So let's pick a triangle like this one. And then refinement essentially says you go and split this triangle into 3 smaller triangles. We're putting a new point at the centroid of that triangle. But if that's all you do, then it turns out you might violate certain other geometric constraints that the triangles everywhere have to satisfy. So what you actually do is you find all the triangles that are going to be affected by this operation. They're set to lie in the cavity of that bad triangle. I've shown that in blue. You remove all of them from the mesh, and then you add new triangles. And some of these new triangles, as you can see, may themselves be badly shaped. Well, you just keep doing it. And since you get tired doing this very quickly, let me just run it for a little while. And then it produces the kind of meshes with pictures you've probably seen. So this is one way of producing what I call guaranteed quality meshes. Okay, I'm going to turn the animation off because in the past I've noticed people just stare at the animation and stop listening to what I say. So, all right. Now that you know what this thing is doing, let's ask the question again. Where is the parallelism? Is there parallelism here or not? Interactive talk. Sure, there's parallelism there.
Parallelism, Professor.
Right. If you have 2 triangles that are far enough away that their cavities don't overlap, you can obviously do them in parallel. On the other hand, if the triangles are close enough that their cavities overlap, you can do them in one order or the other, but you can't do them concurrently. And in a big mesh, you start with lots of bad triangles typically, so there's lots of parallelism, and I'll show you some numbers later. For a reasonable sized mesh, our code actually scales to about 300 on 512 cores. So there's lots and lots of parallelism here, and you can actually exploit it. However, if you think in terms of these parallel loops and so on and so forth, well, these computation-centric abstractions don't really help you. So what is key is this data-centric view of the algorithm, where the pride of place now is the data structure. In this case, it's a mesh. So there are certain elements in this mesh, in general a graph, which we're going to call active elements. So these are elements where there is work to be done. So in this case, the triangles. In other codes, there might be nodes or edges. So there are just sites in the data structure where there is some work to be done. And you can imagine them sort of flashing red, saying, some thread, please come, I'm bad, please fix me, right? Okay.
Keshav,
Yes.
question now or you want to wait?
Please ask questions now.
Based on this animation that you showed, it showed that larger triangles ultimately ended up being very small triangles.
Right.
So do I interpret from there that now the unit of parallelization has become much smaller, and that itself will incur an overhead and sort of cut down into the benefits of parallelization?
No, the overhead is actually independent of the size of the triangle. Because the work that you have to do is simply finding the cavity of the triangle and then replacing all of the triangles and adding new triangles.
So it doesn't have an overhead?
No, it doesn't. But the amount of parallelism starts off, it increases because you're creating more bad triangles than you're removing, and then it dies down as the mesh gets fixed. Right? So unlike in many computational science applications, sparse matrix vector multiply, there's a fixed amount of parallelism that you're dealing with. So here it's very dynamic, so that's part of what makes these codes hard to hack. Okay, so this is what I call a data-centric view of the algorithm. So there's the data structures, there are sites in the data structure where there's work to be done. What is the work? Well, that is described by the local view of the algorithm. So the local view of the algorithm is simply the computation that you do with an active element. So we call that the operator. So in this case, that's applied, the operator is applied to a bad triangle, find the cavity, remove the triangles, retriangulate it. So that's the local view of the algorithm. And then the other thing that you have to tell me is the global view of the algorithm. So in general, I have multiple active elements at any point during the algorithm, and you need to tell me which one I need to do next. So suppose I have just one thread. So are there some constraints on the order in which I can process these elements, or am I free to pick them in any order at all? So in this particular application, it turns out you're free to pick the bad triangles in any order. So you take all the bad triangles, you put them on a work list, and you just process them in some order. Different orders will give you different final meshes. Okay? But any one of those final meshes is an acceptable answer. So this is what we call the unordered algorithm. There are other algorithms like discrete event simulation, which are ordered algorithms, because there the active elements correspond to stations where there are events, and you need to process the events in time order, right? So those are ordered algorithms. For the most part, I'm going to focus on unordered algorithms. So that's the global view, the schedule. This is an unordered algorithm. So in terms of the semantics, any order is fine. However, different orders could lead to different efficiencies. So in particular, if you have just one thread, it turns out to be good to process the bad triangles as a stack. So you take the work list of bad triangles, you take the topmost element off. If you create any new badly shaped triangles, you push them on the stack and you work on them right away. So why is that good for locality? Well, because the new bad triangles you've created are likely to be roughly in the same area of the mesh as the triangle that you just fixed. So you're likely to get good locality, and in fact, using a stack as opposed to random selection from the work list gives you a speed up of roughly 2. So there is a performance benefit from fixing the order that you're going to use. However, as far as the semantics go, you're allowed to do them in any order, and in a parallel implementation, that flexibility is very important to get good performance. So this leads to this view of algorithms. So for an algorithm now in these data-centric terms, there's a local view and a global view. The local view tells you these atomic operations that have to be performed at these sites in the data structure, the active elements, where there is work to be done. And then the schedule is telling you what constraints there are in processing multiple active elements, if there are many of them at any point during the algorithm. Okay, so this is the algorithm. Now, in addition to implement this code on a parallel machine, you're going to need two parallel data structures. The first is a parallel graph implementation. So if I have a graph implementation where in order to modify the graph I need to grab a global lock, well, that's going to be very bad performance. There's lots of parallelism, however, that global lock is going to be contended. Only one thread can get it at a time. So you have to be very careful about the parallel data structure that's implementing this parallel data structure. The other thing that you need to worry about is this work list of bad triangles, because the amount of work that you're doing in each task, each operator application, is relatively small. So if you have 512 cores, they're all going to this work list, pushing bad triangles, getting bad triangles, and so on. Unless you're very careful, that work list can become a bottleneck. And in our implementation, it took roughly 2 years for two of my best students to come up with a work list that actually performs well at 512 cores. So a lot of people talk about the difficulty of parallel programming. What we have found is the difficulty really is in parallel data structures, implementing scalable data structures. If you have scalable data structures, specifying the algorithm itself turns out to be relatively easy. And that's what we're going to exploit when I show you the abstractions that we use in the Kalalau project. Any questions so far? You understand the difference between the computation-centric view and the data-centric view? Okay. So many of you are nodding. You're either nodding off to sleep or it's clear. Okay, now...
So why not have multiple stacks rather than have one stack? That would reduce tension.
No, we do.
512 cores.
Yeah, that's right. So that's how we implement the work list. So as an abstract data type, we just have push and get. But it's actually implemented as multiple stacks inside. And then you have to worry about load balancing because one of these stacks may be empty, so then you have to do steel work and so on. So all of that is done in the system. Okay, so now you might be wondering, well, this data-centric view, is it useful just for these weird algorithms like Iterative mesh refinement that you've never heard about before today, or is it useful for all algorithms? Well, graph analytics has become very popular lately, so let me show you that this data-centric view is actually useful even for understanding algorithms that you probably know very well, because these are some of the first algorithms that we teach undergraduates in data structure courses. So single source shortest path problem, I'm given an undirected graph, the edges have some integer labels on them. Let's assume they're all positive, so this could be a roadmap of Greece. And then I select one city, let's say Athens, to be the start node, so I'm coloring that red, so that's A for Athens. And then the problem is to find the shortest distance from A to each of the other nodes. Okay, so I'm sure all of you have seen this problem before. So in the literature, if you read textbooks, there are lots of algorithms, Dijkstra, Bellman Ford, chaotic relaxation, delta stepping. And the traditional way of thinking about these algorithms, they look totally unrelated to each other. If you look at it in these data-centric terms, it turns out it's very nice because it exposes both the common structure as well as the differences between these algorithms. So it turns out that the way that all these algorithms work, you give a label to each of the nodes, and that label is initialized to 0 at the start node and infinity at all the other nodes. It's going to keep track of the length of the shortest path that you have found so far in the execution of the algorithm. So these labels will be lowered successively as you find shorter paths from A to different nodes. And at the end of the algorithm, the values that you get on the labels will be the distances of the shortest paths from A to those nodes. Okay? So that's called a relaxation operator. So this is the local view of these algorithms. So this is called the relaxed edge operator. And to explain what that does, let me just show you. So this is the only active node initially. So you go process that active node. So if the distance from A to itself is 0, and there's an edge of length 5, then obviously you can lower the distance label of B to 5, and similarly of C to 2. So you apply the relaxation operator. A is no longer active because you finished processing it. But now, anytime you lower the distance label of a node, it becomes active. So it's sort of flashing red over there. Yes. So I'll have to juggle these two things.
Yeah, I know.
But I have 2 hands. So as Vishnu, I'd have 4 or 6. Okay, so sorry.
Comparing yourself to Vishnu now?
Yes. I said both. All right. So these 2 nodes are active. Now, suppose you have only one thread. So which one should you do next? Well, the simplest algorithm is called chaotic relaxation. It just says pick a node at random. So perhaps I pick one here. Okay. So I pick B. So I take this node, I process it, there's nothing to do there, but here I can lower the distance label of D to 12. So now D becomes active, C is still active. So again, I can randomly pick one of them. Let's say I pick D. So then I propagate some values into this sum graph over here. At some point, I pick C. I lower this label from 12 now down to 3. And now again, I have to propagate values over here. Okay, so that's chaotic relaxation. And you can show that if you just keep doing this long enough, you'll ultimately get the correct values. So it's the simplest algorithm. However, it's not very work efficient because it could be exponential. The number of relaxations that you do could be exponential in the size of the graph. So what's a better way to do things? What did the other famous professor from UT Austin tell us to do? Dijkstra's, sorry?
Not use go-tos.
Not use go-tos, that's right. So that guy. So Dijkstra, what did Dijkstra tell us to do? Anybody remember? Nobody remembers?
Do some matrix.
Sorry?
Do some matrix multiplication.
No. That's Floyd Walsh.
Go back to the loop paralyzation thing, and it's probably going to work okay if the graph is dense enough.
No. Here, I have 2 active nodes over here, right? So which one should I pick? If I picked at random, I might pick this one. So if you think about it, the right one to pick would have been C, right? Because that's reached its final value.
Okay.
Sorry?
The shortest.
Lowest cost.
I can't hear you good.
Lowest cost.
Lowest cost, yes, that's right. So what you would do is to pick C, right? And then this would become 3. And then you would propagate that value over here, which is fine. At some point, when you relax B, well, there's nothing to do because you haven't found the new shortest path, so that relaxation doesn't have any effect. So what you need to do is exactly what Guri said. At every stage, the node that you pick is the one that has the lowest label from the set of active nodes that you have. Now this is a dynamic set because you're removing nodes and then you're also adding nodes as they become active. So what is a data structure for maintaining nodes in sorted order when you're adding and removing elements from the set? It's called a priority queue, right? And that's exactly what Dijkstra tells us to do. Maintain a priority queue sorted by the label and always pick the smallest one at each step. So Dijkstra's algorithm is a different schedule. That's the way of thinking about it. It's the same local view, the same operator that you're applying, the relaxation operator. However, the schedule that you're using is not pick a random node, a random active node. You're actually ordering the nodes, and then you're picking the lowest one. Okay, so that's a different schedule, and that turns out to be E log V. So you can see different schedules in this world of unstructured problems can actually make a asymptotic difference, a difference in the asymptotic complexity of the algorithm. Chaotic relaxation can be exponential in the size of the problem. So what's the problem with Dijkstra's algorithm? Well, there's not much parallelism because you're always picking only one node. That's the one that you have to do, the one with the smallest label. So there are other algorithms that people came up with which trade off the work complexity for parallelism. So delta stepping is one of them. So let me give you just a quick idea of what delta stepping is. So this is a fairly complicated algorithm, but if you look at it in these terms, it turns out to be relatively simple. What you do is you take all your active nodes and you sort them into bins. And all nodes that have a distance label between 0 and delta, where delta is a parameter you get to pick, fall in the first bin. Everything between delta and 2 delta is in the second bin, and so on. And what you do is you first work on the first bin, and as long as that bin is non-empty, you're allowed to pick nodes from that bin in any order at all, just like in chaotic relaxation, do them in any order at all. But you move to the second bin only after the first bin is complete. Okay, and so you just keep going until there are no active nodes left. So that's delta stepping. If delta is 1, what does this algorithm become? Well, it's like Dijkstra's algorithm because there's only one level, right? If delta is infinity, well, there's just one big bin, so it becomes like chaotic relaxation. So depending on the structure of your graph, if you have a power law graph, then you can use a relatively small value of delta because you very quickly get to lots and lots of nodes, so there's lots of parallelism. Power law graph, you can use a small value of delta. If it's a road network, you have to use a relatively large value of delta to get enough parallelism. So you can see this data-centric way of thinking about parallelism really simplifies your thinking because you're looking at the local view and the global view of the algorithm, you're separating the two, and there's a lot of clarity to be obtained there. Okay, so for this particular problem, even though this is well studied, this data-centric approach, different schedules, different parallelism, locality, and work efficiency. Okay, let me finish up the examples by showing you that even for these dense matrix computations, this data-centric view is actually helpful. You can use it. So here is a finite difference computation. Let's say you're solving the heat problem in 2 dimensions. So again, you discretize the domain into a 2-dimensional grid like this. So this contains, let's say, the temperatures at some time t, and then the temperatures at time t plus 1. You compute by taking, this value is computed by taking the weighted average of the values of its nearest neighbors. So again, you can see a local view and a global view. What are the active nodes in this algorithm? Well, all of these nodes in the time step that you're working on, they're the active nodes. So what is the operator? What is the local view? Well, the local view is simply the stencil that you're doing. And then the global view just says, what order do I fill these elements in? And different orders have different amounts of locality. In this case, the asymptotic complexity doesn't change. So it's a simpler world of dense linear algebra. However, you get different amounts of locality depending on the schedule that you use. Now, this is what people call a regular application. This is one of these HPC applications that can be parallelized at compile time. And the reason for that is that the grid structure is very simple. Right? It's a grid. The only thing you don't know is the size of the grid. Everything else you know at compile time. You also know that you're filling all of these nodes, so you know all the active nodes, you know the neighborhoods, you know the grid structure, so you know everything other than the size of the problem. And so at compile time, you can actually take the code like this, and then you can use all of these nice integer linear programming techniques to analyze the program, find the parallelism, and so on and so forth. Okay? So it's just because things are very simple here. Okay, so at this point, let's summarize, put it all together, what we've learned so far. So this is what we call the operator formulation for algorithms. It's a data-centric view of algorithms where you look at data structures and operations on data structures. So there are certain elements in a data structure where there's work to be done. That's what we call active elements. So usually there are nodes or edges. The operator is this local view of the algorithm that tells you what computation you do at an active element. So usually that computation is going to read and write a small portion of the graph around the active element, like here. We call that the neighborhood for this particular activity. It's usually distinct from the immediate neighbors in the graph. And we support arbitrary neighborhoods in Kalalau, as I'll show you. And then, as we said, in general, you're going to have lots of active elements. And so you need to say something about scheduling constraints on how I can execute these activities. So in unordered algorithms, the implementation is allowed to pick these active elements in any order at all, although different orders can give you different amounts of efficiency, but semantically, any order is fine. So there's a lot of flexibility. They're easier to parallelize for that reason. And most of the algorithms that we talked about today, like the finite differences, Kalalau mesh refinement, chaotic relaxations, all of them were unordered algorithms. And then you have this more difficult class of ordered algorithms like discrete event simulation, where you're allowed to do the activities in any order, but ultimately it must appear as though they got done in some algorithm-specific order, like, for example, time order. Okay? So those are harder to analyze. I'm not going to talk about those today, but this is what we now call amorphous data parallelism. So in this data-centric way of looking at algorithms, parallelism arises because you can process multiple active nodes in parallel subject to these neighborhood and ordering constraints. And so this is what leads to that motto, which is the title of my talk: parallel program is operator plus schedule plus parallel data structure. You can look at locality also. For lack of time, I'm going to skip over that. What time do I need to end?
12:20 according to the schedule, but Luigi is the boss, so he may want to give you more time.
12:05.
I'm sorry?
12:04 now.
12:20.
Sorry.
Okay, good. I can keep going for 4 or 5 hours.
No.
Half an hour. Okay, so that was this operator formulation of algorithms. Let me quickly go through parallelization strategies, because as we said, our view of parallelization strategies also changed over the years. So there's static parallelization, where you can find the parallelism at compile time, and then all these other ways of finding parallelism. So the parallelization strategy that you can use for a particular algorithm depends really on when you know the active nodes and neighborhoods. So in the simplest algorithms, like the finite difference stencils, you knew the active nodes and neighborhoods at compile time. Because I tell you it's a grid, you're going to fill in all the elements of the grid, so you know the active elements, you know the stencil, so you know the neighborhoods, etc., etc. So everything is known to you other than the size of the problem. So you can take all parallelization decisions, as with the parameter being the size of the problem, and so you can do compile time or static parallelization. And that works for these HPC codes, like stencil codes, FFTs, where you draw that butterfly diagram and so on. So everything really is known. Because we came to parallel computing through the HPC world, we sort of assumed when we started that this was the default for all algorithms. And what I'm trying to convince you of today is that that's actually not the case. So in this unstructured data world, where you're dealing with these graphs which could be changing and so on, really you can't do static parallelization. You have to find the parallelism at runtime. And so one way to do that is by using speculative or optimistic parallelization. So if you know the time warp algorithm for doing discrete event simulation, well, that's exactly what time warp does. So it uses speculative execution. And then in between, you have different binding times. So for some algorithms, you can't find the parallelism at compile time. However, once the input graph is given to you, because the structure of the graph is not changed by the algorithm, you can pre-process the graph, find activities that don't conflict, and you can come up with a parallel schedule before you run the algorithm at runtime after the input is given to you. So that's a very old technique that's called inspector executor. So this is, again, all of this gets unified in this data-centric way of looking at things. I'd be happy to talk to you about these parallelization strategies and so on, but I don't have time because Luigi is going to pull the plug. Okay, now let me tell you about the system. So I've hopefully told you a little bit about the motto that I have. So parallel program is operator plus schedule plus parallel data structures. Now how does this help us in terms of coming up with abstractions for this world of ubiquitous parallelism, where a small number of Stephanies have to support lots of Joes? Well, here is what we do. So in the Galois system, the Stephanie programmers were my graduate students. In fact, a relatively small number of my graduate students were really, really good at parallel programming. What they have done is to build a library of parallel data structures, like a parallel work list data structure with different policies for getting elements from it. Similarly, parallel graph data structure. So we have many different implementations where the nodes and edges are stored in different orders for different kinds of locality. But they all support a very simple API. So for work lists, it's just put and get. Get active element, put a bunch of active elements when you create it in work. Similarly for graphs, it's just give me a random node or give me the immediate neighbors of a node, give me the outgoing edges, incoming edges. So the API is very simple, very straightforward. So you don't think in terms of concurrency or anything at all, but underneath it's all implemented using a lot of very sophisticated parallel programming. And then we also have a runtime system. So in addition to the library of data structures, there's a runtime system that does dynamic load balancing with work stealing and so on. So you talked about having multiple stacks. So one of the stacks goes empty. Well, what do? You have to go steal work from all of that is done transparently for you by our system. So what does Joe have to specify? Well, Joe is the guy who specifies the algorithm. That's your job, after all. So we give you the data structures and the runtime system. You specify your algorithm by telling us the operator, the local view of the algorithm, and then the schedule that we have to use for processing different active nodes in code. So Joe codes actually in sequential C++. So a Galois program is a legal C++ program that you can actually execute sequentially. However, you can also execute it in parallel on a system. And to do that, what you need to do is to use a construct that we give you. So it's not just some random C++ code. You have to use what we call a Galois set iterator in order to highlight opportunities for exploiting this amorphous data parallelism. So let me show you that on the next slide. So Joe writes a program that looks like this. So this is, imagine this to be a C++ program. And then you use the set iterator in order to highlight opportunities for this amorphous data parallelism. So if it's an unordered algorithm, what you do is you create a work set with all the active elements, and then you say, for each active element, do whatever it is. So the body of this iterator is the operator, because that's what you're doing on each active element. And then we give you a small DSL for specifying the schedule that you want to use for the different active elements. So you decorate the iterator, like you do in OpenMP, for example, with the schedule. So that's how you specify the schedule. And the body over here, which makes calls to these graph data structures and pushes work and so on and so forth. That's the operator. Okay? Okay, so now how do we execute this program in parallel? So there's a master thread that begins the execution of, yeah.
So Joe still should have an understanding of his data structures and algorithm, but he doesn't need to know how to efficiently implement this.
How to implement the data structures.
Yeah, he doesn't need to know that, but he needs to have some idea of...
Yes.
Yeah.
You have to pick the right data structure. So this is one of the things you do have to do.
Yeah.
So ideally, Joe can be a domain expert.
Yes.
The problem.
That's right, that's right. Okay, so now how do we execute this program in parallel? There's a master thread that begins the execution of the program. When it gets to one of these Galois set iterators, it says, there's an opportunity to exploit this amorphous data parallelism. It creates a bunch of worker threads, and then all of these threads basically go to this work list that you created outside the iterator. So these are just all the initial active nodes that you have, like the initial bat triangles in that mesh. And then each one basically just grabs some active element, starts working on it, starts making calls to the graph API. And so it's going to touch more and more of the graph. So it's neighborhood in the graph. Now what you need to do is to ensure serializability of these iterations, because we said each of these operators has to be done atomically. It should be transactional, right? So it should appear to have been done instantaneously without any interference from anybody else. So what happens is anytime you make an API call to the graph API that we give you, like for example you say, give me all the immediate neighbors of the active node. Before we return that set of neighbors to you, those are locked on your behalf. So imagine that each thread has a color, so all of that portion of the graph is basically colored for you by the data structures before our parallel data structure implementation, before that set is returned to you. So that's transparent to you. So as the thread is executing, as this activity is executing, there's a larger and larger portion of the graph that's colored because you have touched that portion of the graph. When the activity completes, all of those colors are released, and then the thread goes, grabs another active element, and so on. Now the question, of course, is what happens if there's a conflict? So you make an API call, I want to return some subset of graph elements to you, but they've already been colored for some other thread. So that's when neighborhoods overlap. That's when the runtime system kicks in and it rolls back one of the activities, lets the other one continue. So we have ways of avoiding deadlock, light block, all of those sorts of things, but this is essentially how speculative or optimistic parallelization is implemented in our system. Okay? So that ensures the utilizability of the iterations, and we've implemented both this speculative or optimistic execution and also another approach that's called interference graphs, which we use because in some applications you want deterministic results. So remember when we talked about Delaunay mesh refinement, we said depending on the order in which you do the bad triangles, you may get different answers. So one of the annoying things about this speculative execution strategy is that each time you run mesh refinement, for example, you may end up with a different mesh. And we've had people who said, no, this is driving us nuts, we want the same answer and we're willing to pay a little price in terms of performance. So we have a way of, without changing anything in the programming model and so on, basically returning answers to you deterministically. So every time you do DMR, you get the same mesh back. Okay? So I can talk more about this if you're interested. Okay, Luigi, you're looking upset. Let me go on. Okay, so I had that's a small Galois program. The key point is there are no threads, etc. Right? So you're writing Joe code. Okay, so let me finish up by showing you some results, and I'll start with results from other people because they're always a little more plausible than results that I present about our own system. So this is an Intel study that appeared in SIGMOD, which is this database conference last year. So what Intel did was the following. They took the Galois system, and then they also took a bunch of these graph analytics frameworks, like COMBLAS, which is from John Gilbert at Santa Barbara, GraphLab, which is very popular in the machine learning community, and Giraffe, which is from Facebook. So these are all graph analytics frameworks. We just do graph analytics. Analytics means the structure of the graph doesn't change. You're just propagating labels. You're updating labels with nodes and edges. Okay, so things like that, single source, shortest path problem. But you're not doing things like Delaunay mesh refinement and so on, where the structure of the graph itself changes. So that you can do in Galois, because Galois is not necessarily, it's not really a graph analytics framework, it just does all kinds of graph problems. But you can use it for graph analytics too. Now, in addition to writing these kernels like PageRank, breadth first search, and they had a bunch of others like a recommendation system and so on, they also had their engineers write code using pthreads with atomic instructions and all of that. So that's what they call the native code. And then they took different input graphs, because in this world, performance can change very dramatically depending on the structure of the graph that you give it. But all of these are social network graphs. They're not particularly big by the standards of what we do nowadays, but all of them have roughly about 10 million nodes and about 100 million edges, right? That's the way to think about it. Okay, then the y-axis is basically, think about it as performance. So lower is better because it's time. Okay, and then the other thing to note is this is a log scale. Okay, so for lack of time, let me just show you breadth first search numbers. So the blue lines over here, that's the native code written by their engineers. The red line over here is the Galois code. And what you notice is that for the most part, it's more or less comparable. So they gave a factor of about 1.2 to 1.5 slowdown of Galois with respect to native code. So that's the abstraction penalty that you're paying, but it's respectable. These big lines over here, that is Giraffe. So that's Facebook's graph analytics system. It's built on top of Hadoop. If you know Hadoop, it does I/O, right, for fault tolerance and so on and so forth. So, giraffes have long necks, and so, giraffe lines are rather high, so, they're tens of thousands of times slower than everybody else. And then in between, you have these other systems like GraphLab and so on. And the point to note is that we do respectively compared to all these other graph analytic systems, even though Galois is not a graph analytic system per se, right? You can do it, but you can do other things.
Just a short question.
Yeah.
Do you have the numbers of the differences in the number of lines of code that you have to do in native and
Yeah,
in this case?
that's all there in the paper. So I can forward that to you, or you can.
No.
So I want to look at the two interesting cases, which is native versus Galois.
Okay,
Galois is Joe programmer doing the job,
great.
but supported by Stephanie.
Yes.
What happens if you give Stephanie the job you're giving Joe?
If you give Stephanie the job you're giving Joe, so you have an expert programmer writing Galois code. But you still have to use the abstractions. That's the difference between native and what you're asking?
Yeah. No,
Yeah,
so what I'm wondering is if Stephanie starts with the algorithm at the top
Right.
and has the ability that Stephanie has, that Joe doesn't have, can she do a lot better than Joe using the support from Stephanie?
Yeah, in some cases you can, and that's mainly because of the choice of the data structures. So for example, you need to know a little bit about how a parallel program actually executes to know which the right data structure to use is for good locality, right? And so we found that naive programmers very often use the simplest data structures as opposed to a more complicated one that gives you better locality. So you have to make the right choices for the schedule and for the data structures. So yeah, the answer is yes. But in this case, these kernels are simple enough that it did make a difference. Okay? All right, so the takeaway message from here, and they have a lot of results in their paper, but basically, we do respectively compared to pthreads code, explicitly parallel code, and so on, and we do substantially better than all of these other systems. Okay. These are more numbers, and yes. Question. This doesn't count for my time.
No, of course.
That's good. Yeah.
The pthreads guys, did they use the Galois concept, or they use the?
No, they were allowed to do anything they wanted to. That's right. They coded with pthreads, atomic instructions, and all the rest of it.
But the programming concept, did they implement it?
Using this data-centric idea and so on?
Yeah.
I really don't know. So this was done at Intel, we just got the paper.
Exactly. So this could be meaning that if they actually use the I will call it the parallel 4 concept, then it's really impressive, because you probably didn't do a lot of low-level optimization, right?
No, there's no opportunity to do low-level optimization because this is Joe code. Let's take that up offline. And if you have questions, I can give you the paper and you can contact them. So it's pretty two-ways. Okay, so these are more numbers from a SOSP paper that we published. And the difference between the previous graphs and these graphs is that these graphs also show you what happens with road networks. So as we said earlier, social network graphs have low diameter because you start from a node and you very quickly can touch most. So the breadth first depth is very small for social network graphs. So they tend to be easier to parallelize than road networks, which have a relatively high diameter. So a lot of these graph analytics frameworks are tuned for these low diameter social network graphs. If you give them a road network, they basically die. Okay? And that's sort of what these numbers are showing you. So here we're comparing against Ligra, which is from Guy Belloc's group at CMU, PowerGraph, which is a version of GraphLab, the latest version of GraphLab, which is very popular, as I told you, in the machine learning community. And here you start to see differences of about 10,000 in terms of running time, because they really don't do these high diameter graphs very well at all. There's a lot more to be said over here, but let me skip over them because that's the main takeaway over and above the previous set of graphs. Okay, all of those results were done on 40 core machines, which are fairly small nowadays. So these are numbers on a 512 core SGI origin. So it's a big shared memory NUMA system. And what I'm showing you over here is scaling. So this is not speed up compared to a serial implementation. It's just self-relative performance compared to single-threaded Galois code. And I just wanted to show you the non-mesh refinement, which when we started was a very difficult code, wasn't even clear there was parallelism. So what you notice is you get a scaling of about more than 400 on 512 cores. So this is, even though it's irregular, you're writing joke code, you're really getting good scaling. But those of you who do parallel computing know it's very easy to cheat with scaling because it's self-relative. If your single-threaded performance is very poor, you can get good scaling, but the time to execution might be very bad. So here, what we've done is compared against, you probably can't see this at the back of the room, I apologize, but this is the DMR line, and we compared against Triangle, which is a code from Jonathan Shuchak, a computational geometry guy, who has a very well-known code called Triangle for doing generation of triangular meshes and refinement, DMR. And so what you notice is that it's a serial code, but it's highly tuned just for this one application. And so on one thread, for this particular input, Triangle takes 96 seconds, Galois one thread takes about 160 seconds. So there's roughly a factor of 2 slowdown, because ours is a parallel code and the data structures that you're using are not tuned for mesh generation and so on. But since we have a parallel code, by the time you get to 512 cores, our execution time is about 0.37 seconds. And so compared to Jonathan Shuchak's serial code, there is roughly a speed up of about 300. Right? So it's not as impressive as the 400 of scaling, but it's a real speed up of about 300, which is respectable. And then there are other lines for triangulation, advanced HUT, etc., etc. Okay, I'll wrap up with some other results from other people. So recently I was visiting UC Riverside, and I ran into a guy there named Philip Brisk, whom some of you might know since he's in the embedded FPGA world. And so he said they had downloaded Galois and used it in order to do FPGA routing. And what they did was to compare against VPR, which is apparently a placement and routing tool that everybody uses in the academic community for doing FPGA placement and routing. And bottom line is that, so these are different circuits, running time, so lower is better. So VPR on the average over all these takes about 125 seconds, Galois 8 threads, so 22. So we're talking of roughly a speed up of about less than 7, between 6 and 7 on 8 threads. Now this is the non-deterministic code, right, which will give you different routes every time you run it. So these guys, when I visited them, they said, you know, we're getting good speed up, but we get a different route every time because of the non-determinism in the speculative execution is driving us nuts. We said, okay, we just implemented a deterministic version of this using interference graphs. So we gave them that, and then for that they get less speed up, so it's about between 5 and 6, but it's still respectable because this is something that we didn't have anything to do with. They just downloaded the system, used it for this application that we didn't even think about for Galois. They have a paper at DAC in 2014, so parallel FPGA routing based on the operator formulation. So that's what I'm trying to sell you. So we have at least one customer who likes operator formulation. Okay, let me skip over these. Okay, let me just summarize. Okay, so I told you about a bunch of things today. What is the message I want you to take away? If there's one motto that I want you to take away, it's this motto, which many of you probably can't see, but you've heard it several times today. Parallel program is operator plus schedule plus parallel data structure. It's a useful way of thinking about parallelism. You separate the algorithm from the data structures. You probably know Niklaus Wirth's motto, program equals algorithm plus data structure, so we're sort of playing off against that. So for a parallel program, what we're saying is you need a parallel algorithm and a parallel data structure, but the parallel algorithm is useful to decompose it into a local view, which is the operator, and then a global view, which is the schedule. So that's where the data-centric thing really helps. And then what we're saying is really the complexity of parallel programming, once you see it this way, lies mostly, in our opinion, in building good scalable parallel data structures. And you see this even in sequential C++, for example. So the STL library it's a big data structure library, and people just use that. So even in the sequential world, people recognize the data structures are where the really hard problems are. So we've sort of encountered the same idea. So we give you this parallel data structure library with a runtime system, and then you have to specify the operator and schedule. So we started with a computation-centric view of parallelism, and I hope I've convinced you that this computational-centric view worked reasonably well in the simple world of HPC programs, where everything was regular and you're working with dense matrices and vectors. When you get to these unstructured data problems, it really doesn't help you. And I think this data-centric view, this operator formulation of algorithms, is a nicer way of looking at algorithms, and it leads naturally to this abstraction that we talked about, which was necessary for ubiquitous programming, where the Stephanies build the parallel data structure libraries at the runtime system, and then the Joes can use relatively simple notation, sequential C++, for example, to write the operator at scale. And where we're going with this is when we talk to people using our system, they say even C++ is too complicated, we hate this stuff, really we want even simpler notation. And so what we're trying to do now is to layer DSLs on top of the Galois system. So from the DSLs we would generate the C++, which then runs on top of Galois, or maybe we go lower, not sure yet. So these are the things that we're just starting. And then I want to emphasize this is still a shared memory system, so we know what to do with GPUs. We've got a bunch of papers, but right now it's an alpha, and then distributed, so distributed, heterogeneous, that's the place where everybody's going. Okay, so all of this is the work of lots of people, and so I want to thank in particular Andrew Lenhart and Donald Wen. So Donald I need to update the slide, Donald just finished his PhD, and he's off joining a startup somewhere. But these are my two Stephanies. Okay, so these two guys built the whole system. Don't try to steal them from me. So maybe I shouldn't be telling you this. But the rest of them are very good, but really expert parallel programming is very, very hard, right? So the only two guys in my group were really good enough to be able to do this kind of programming. And then we have visitors from all over the world. One of the nice things about being in Texas is that there's a lot of internal money to support visits from people and so on. So if you'd like to visit our group, please do come. So right now in my group we have visitors from Norway, Poland, and China and a bunch of other places. So we welcome visitors. This is our homepage, and on that homepage you'll find a bunch of benchmarks, which we call the Lone Star benchmarks. So everything in Texas is either Lone Star or Longhorns, right, which is the football team. So Lone Star benchmarks, so these are all a whole bunch of graph applications written in Galois, which we distribute along with the system, and then all of our papers. So thank you so much, and Luigi actually finished my class. Guri is going to ask a hard question. His job is to harass all the keynote speakers.
It's what you observe is as people start using parallelism, they want to go towards sequential. They want to have a sequential view of the world. The deterministic guys.
Yes.
All the Joe programmers, they want to have a sequential view of the world. So why not give them a sequential view? Under the hood at Galois.
Under the hood?
Yeah, give them a completely, totally ordered sequential.
No, over the hood. Over. So what he's saying is on top of Galois, given that sequential model, which I agree with. I would say to raise that orange bar he had,
Yeah.
raise it higher.
Yeah.
That is, make the job harder for Stephanie because Stephanie can take a harder job. Make it easier for Joe because Joe can't.
No, I think, okay, I think I know where Guri is coming from.
Oh.
One of his students visited my group and gave a talk on their work, and so I know where he's leading to. What he wants to do is to eliminate these unordered algorithms altogether and work only with ordered algorithms.
No, we have the unordered algorithms, but give an ordered execution of the unordered.
No, give an ordered execution, fine. Okay.
Yes. And so the reason being is that there is none of this non-determinism and all that other stuff. And it makes everything look like it was sequential, totally ordered, and you know, in the superscalar processor has been an excellent example of how you do everything under the hood, above the hood, everything is sequential, life is good, and everything works. And for parallelism to proliferate, I claim you have to do that for software too.
Okay, so Guri, I think I would say two things. The first is that these unordered loops, right? You encounter those even when you're writing sequential programs. Because if you open up a book on algorithms, right, you'll find two kinds of these graph algorithms. One set of graph algorithms say, create a work set, and while work set not empty, do. And you haven't said anything about the order in which those get processed, right? So those are what we call unordered algorithms. The other class of algorithms, you say, build a priority queue, while priority queue not empty, do. And those are what we're calling ordered algorithms, right? So at some level, I think the notion of an unordered algorithm, namely an algorithm is working on sets, right, as opposed to sequences, is a very natural idea. Now what you're arguing is more sophisticated than that, because you're saying, I'll let you program with sets, however I'm going to guarantee that it appears as though those elements were processed in a deterministic order every time you run them.
Correct.
Right? Yeah. So we do support that, right, with this interference graph approach that I was telling you about, that we use for this FPGA routing, for example. And we had a paper in ASPLOS last year on how we do this deterministic scheduling. But there are 2 points to make. The first is, I still think the notion of, I'll accept any answer that you give me, even if it's different for each runs. I think that's a useful idea to have. So we're not taking away anything if you want your world, right? We're just giving you something extra.
Thank you.
So, can you show an example, maybe you did and I missed it, of concretely how does a schedule look like? Because Joe has to write a schedule, right?
Joe has to write the schedule,
And
that's right.
I don't, did you show us a concrete schedule? How does it look like? And many schedules, I suppose, are dynamic.
Yes.
So
in this world, everything is dynamic.
Yeah, is it easy to write dynamic schedules? Because it seems to me that Joe is becoming a little bit of a Stephanie now in your approach.
Okay, very good. So, so the question, to repeat the question and to give me a little bit of time to think about it now. Okay, so to repeat the question, what you're asking is, how do you write schedules in the Galois system, and is it easy to write these schedules given that you need these dynamic schedules, by which I mean, I assume you mean things like FIFO, LIFO, and things like that, right? As opposed to what you have in OpenMP, which is just static chunking, for example. Right? Yeah. So the answer is no, I didn't show you an example of that. And B, it is non-trivial to come up with a good schedule, right? Because you need to have a very deep understanding of your algorithm and so on, because you have to trade off work efficiency for parallelism. So even something as simple as single source shortest path, what I showed you was you need that delta parameter, right? And unless you set that delta parameter correctly, you actually can get very poor performance. And so, we've seen papers comparing our system with other systems, and sometimes we look bad, and then we look at it and say, gee, what's going on? How come we screwed up so badly? And it turns out they used the wrong, there's a default value of delta that we give you, and sometimes these folks just run it with the default value because for their particular graph, that's the wrong value of delta, and they don't care about tuning the delta, right? So, yes. I think to simplify matters further, we need to look more into the schedules and how we might automate coming up with some of the schedules, but that's a deep property of the algorithm, so I don't really know how easy that's going to be to automate. And then the final thing that I want to point out is we have a paper in ASPLOS back in 2012 where we talked about a DSL for specifying these schedules, right? So it's there, and I'm happy to, if you send me mail, I'll send you the paper. That's what we support in the system. And the way we came up with that DSL was by going through the literature, looking at the different kinds of schedules people were using for things like preflow push and all the standard algorithms, and then trying to come up with a DSL that could express those schedules. Now, one question that I often get is, well, how do you know that this DSL is it, and that maybe tomorrow there's some graph algorithm for which I want a really fancy schedule, I can't express it. well, okay, then get in touch with us, and if you have an interesting application, we'll add it to our DSL, but I don't know anything else that we can do at this point. Okay, but that's a very good point. People do find it hard to come up with schedules because you have to have a good sense of work efficiency, locality, parallelism, and so on. So that is one of the issues. It has nothing to do with Galva per se, because even if you're writing pthreads code or something, right, you do have to worry about those issues.
Has everything to do with Joe.
But it has to do with Joe, it has to do with the algorithm. That's right.
And that's why Guri's point is well taken. That Joe has to be protected from all this stuff.
No, but this, nobody can protect you from coming up with the right schedule, because preflow push, for example, there are entire papers written comparing different schedules and things like that. It's a very deep property of the algorithm. I can.
Algorithm expert.
Yeah, it's an algorithm. Yeah, Joe has to be an algorithm expert.
So my second question, two questions. So my second question is pretty much on this line. So how competent is Joe, not in the application of the algorithm, but on actually understanding parallel systems, right? That's the physicist spending their life programming parallel systems.
Yeah.
He's less than that. How much less? But that's probably being addressed here. So how does what Joe has to do and identify pieces of code that is the operator? How does this compare to task-based programming, parallel programming? Is this a task?
It's a task.
And then
It's a task.
so
That's right. So the operator application, what we're calling an activity, is a task. That's right. But your deeper question is, it's another great question, which is, okay, I use this system, I'm a Joe, and maybe I'm a reasonably sophisticated Joe. I'm not a Stephanie, but I'm a Joe++ or something. And I write the code, and then I get bad performance. What do I do, right? How do I understand where the bottlenecks are? So this is another thing that we're spending time on, because we do have people who use the system, and then they say, or my own students who are not Stephanies, right? So they're asked to produce a benchmark for our benchmark suite. They do something and they have a bottleneck somewhere, and then they have to go running to my Stephanies and say, oh, help, do something here, right? So yeah, I think that is the next thing, the next big problem that I think needs to be solved by the community, which is what can we do to understand parallel performance in a way that makes sense to somebody who's not necessarily a real expert. What do we do right now? Right now we use VTune. It's a wonderful tool. It tells you where the bottleneck line of code is, so then we stare at that line of code, and my Stephanies together with the Joes and so on and so forth say, oh, you know what's actually happening over here is it's a Numa effect, because you're doing an atomic operation on a location and it's bouncing between caches. Okay, so you need to have a fairly sophisticated understanding of architecture and so on and so forth to come up with those sorts of diagnoses. So I think that is the sort of a big unsolved problem, which is take the VTune results and somehow present performance bottlenecks, etc., in a way that makes sense to Joe. Now, there is a project at UT Austin being done by Jim Brown, who's a very distinguished senior member of the CS faculty there. So he's been working with Intel to come up with a tool whose name I'm now blanking, PerfExpert, I think that's what it's called. So it's called PerfExpert, and what it does is it takes all the VTune results and distills out something for you so that it makes sense at the Joe level. Unfortunately, that tool is focused only on these dense linear algebra codes. Because that's what everybody understands, right? Dense linear algebra.
Does this tool split it in terms of requirements for the operator improvement, the requirements for the schedule? So this will be nice.
That's right. But Jim doesn't think in terms of operators and schedules, because he's coming from this regular world where you have do loops, and so it's Fortran code, do loops, nested loops, etc., etc. And so his tool actually recommends loop transformations for you. So it says, you'll get better locality if you interchange these two loops, if that's legal. So things like that, which I think is very useful, and it's being supported by Intel, and there is apparently some interest from Intel in taking it and putting it on top of VTune and so on. But it doesn't address any of these problems that I'm dealing with, which have to do with unstructured data. Right? But some tool like that along those lines, I think that's the next sort of frontier that would be wonderful to have people working on.
You have an equation up there.
Okay, yes.
And I was thinking of about a relation rather than an equation. And I don't know whether it's greater than or less than. On one side is Joe plus plus,
Yes.
on the other side is Stephanie minus minus.
Okay.
And which way does the relation go, greater than or less than? I think finding where to put this thing is critical.
And so to answer the final question that you had asked me before I started my talk, which way, so I don't know if you guys can see this, but it's plus and plus over here. And Yale said, well, which way should I associate this? And the answer is, it's left associated, so operator plus schedule, that's your algorithm, and then you get the parallel data structure. Thank you, way over time. So, thank you.